Okay, there's a couple of final things about viscosity we should take a look at. The symbol for viscosity that we talked about earlier was a mu. Um, it came from this equation, and the units, I'll just put this out here, the units are generally in something called, well, we'll just say, we'll cover them in both, pounds second over feet squared, or Newton second over meter squared. That makes sense if you look at it, because the units here are in, let's just work in here, pounds per foot squared. The units of this is, if you look at it, it's feet per second, and this is feet underneath here, so you have a lone second over here. So if you move this to this side, you get pounds second over feet squared. However, there is another viscosity that is talked about a fair amount, and let me show you why it's important. And with that, we have a distinction between these two. Here, this is called the dynamic viscosity, and we have another one, and I'm going to attempt to do a decent job of this, but the symbol is somewhat looks like that, and it is called the kinematic viscosity. Now, what's the difference between these two? And it's pretty simple. The kinematic viscosity is nothing more than this. Now, why would you even define something like that? And here comes a good reason to pick this up, and I'm going to introduce this, and then I'm going to backtrack on myself. But one of the most common numbers that exist in fluid mechanics is called the Reynolds number. Now, we will get into this a lot more later, but the Reynolds number is generally for pipes, is defined, and usually it's written something like that, and it's defined as rho, the velocity in the pipe, diameter of the pipe, over the viscosity. And generally speaking, it's the dynamic viscosity. So you can see right off that you could write this number like this. So as it turns out, Reynolds number is the first occurrence that you might see something like that. It's somewhat repetitive in the tables. If you go into the tables, you'll find a column for rho, a column for mu, and then a column for the kinematic viscosity. So you don't need this one if you have these two. You just divide this number by that, and you have this column. So it's kind of redundant. But still, it's easier just to look in there and find your number if you need it. So let's just say we had a particular case in which we had a diameter of a pipe, that was, say, 0.1 feet. We had a density which was 1.94 slugs per cubic foot. We had a viscosity. This, by the way, is for water, and if that's for water, we might as well make the other one for water, and it ends up being about 2.34 e to the minus 5, and it's in its pounds second foot squared. And say the velocity running through this pipe. Now you have to realize All these, okay, wait a minute. These are properties of the fluid. This is geometry. And this is the flow, say, conditions. So if you're running water through a pipe, it doesn't matter what the diameter and velocity is, you always use these for the dynamic viscosity here and the density. Somebody tells you the diameter, or you know the diameter of the pipe. Now you're looking at just a flow. So let's say we had, just make our life easy, feet per second. If we want to calculate the Reynolds number, it's just fairly simple. Rho, let's grab the rho, 1.94 slugs per foot to the third. Now let's grab the velocity, 1 foot per second. Let's grab the diameter, 0.1 feet, and let's slide under there, 2.34 e to the minus 5 pounds second over feet squared. Now we can figure out our numbers, and if we want to do that, what we'll find roughly 8.290. But now let's look at our units. This is the key right here. If we're looking at our units, we'll say we have a slug. I'm going to start moving things around, okay? If I have a foot here and a foot here, that gives me just a foot underneath. Now I have a second down here, but I also have this second. To move this foot squared up here, and I can end up clobbering some stuff out, but I have a pound under here. So I'm sort of stuck, okay? Now if I knock out one of these feet with one of those, but your key here is, and we've seen this earlier in this section, is you have a mass stuck in here with a force, so you need to get rid of those. Remember, F is equal to ma, so force is equal to a mass, and then A is nothing more than feet per second squared. So if you want to convert this non-dimensional term, you could say a pound is equal to a slug, a foot, and then a second squared. So why don't we stick that in there? You stick that in there, and you're putting in here slug, carry this out, feet, and then since this is second squared, you could put it up here. Then what you have now, this slug cancels that slug, this foot cancels that foot, and that second squared cancels that second squares. So what you have is no units. Here's the key. The Reynolds number is a non-dimensional number. And as a result, we'll find later, it's extremely powerful indicator of the flow and how it behaves. Now, that's not to say all non-dimensional numbers do that. There are specific non-dimensional numbers in fluids which have extreme significance. Reynolds number just happens to be one of these. But this particular Reynolds number is why, in review, that you end up with a couple of different descriptions of viscosity. More often than not, I will tend to stick with this one because, you know, we've already talked about density. If we start talking about this and drop the density, then sometimes that's not the full picture.